So good morning, everyone. In the previous lecture, we have covered the Karush-Kuhn-Tucker method to solve constrained optimization problems. So what we have looked at was the problem of minimizing some objective function subject to inequality constraints. And we said that we can solve this optimization problem, meaning we can determine the optimal solution, which is denoted by X star, by solving the system of equalities and inequalities. And this system you should remember really well, because basically the Karush-Kuhn-Tucker method is the basis of most, if not all, modern optimization algorithms. So all algorithms that you will use in practice, in some form or the other, solve this system of equalities and inequalities. And the first one is the stationarity equation, meaning when we take the Lagrangian and we take the gradient of the Lagrangian with respect to optimization variables, then the gradient should vanish at the optimum. So this is the typical optimality condition that we have seen also in the unconstrained case. But now, since we are also considering constraints, additional conditions have to hold. Primal feasibility means that the optimal solution has to satisfy original constraints, which is quite natural. The second condition is that the Lagrange multipliers that we use in the Lagrangian, they must be only non-negative. And the last condition says that at the optimum, this term here should disappear from the Lagrangian, such that minimizing the Lagrangian actually minimizes the original cost function. And this last condition is called complementary slackness. And this is actually the main complication of the Karush-Kuhn-Tucker method. All these conditions are rather easy, but this one is nonlinear because it involves multiplication between optimization variables. So lambdas as well as the x here, they are optimization variables, so we have a product of them, and we know that the product is nonlinear. So we don't know how to effectively solve this equation here when we have a product in there. Okay? But we know at least something. We know that for certain cases, the value of the corresponding Lagrange multiplier in this complementary slackness condition is 0. And the case when lambda is for sure 0 is when the corresponding constraint is not active. A not active constraint means that we essentially have strict inequality here. Okay? And then for this product to be 0, if we know that the constraint is not active, meaning this term here is negative, for the product to be 0, lambda must be 0. Okay? But the converse, meaning the opposite direction, does not hold, which means that we can have the constraint active, and a constraint is active when it's satisfied with equality here. So this term can be 0, and then actually the value of lambda can be arbitrary, so it can be 0, it can be some non-zero value, as long as it is non-negative. And so this is a general procedure which allows us to solve arbitrary optimization problems, well, under the condition that the objective function and the constraints here are continuously differentiable. So that's pretty much the only condition that we have. However, these conditions in general are only necessary, which means that, yes, the optimal solution has to satisfy this set of equations and inequalities, but there can also be other points which are not optimal, and they will still satisfy this equation here. So they can be, for instance, saddle points or some other strange points in the solution space. So in general, if we have a non-convex problem, meaning these functions here, either in the constraints or in the objective function, are some strange non-convex functions, then this method is only necessary for existence of the optimal solution. However, it can be shown that if our optimization problem is convex, and the problem is convex if two conditions are satisfied. First, the objective function is a convex function, And second, each constraint that we use here is also a convex function. Under such condition, we are talking about the convex optimization problem. Then these conditions are also sufficient, meaning if we find a point which satisfies Karush-Kuhn-Tucker conditions, then the point is guaranteed to be the optimal solution. Okay? So in the general case, more than the optimal solution, so more points than the optimal points can satisfy this system, and we don't know which of them is the optimal. We need to check that based on the value of the objective function at those candidate points. However, in the convex case, we only have as a solution those points which are optimal for our optimization problem. Okay? And as I said, this Karush-Kuhn-Tucker approach to solving optimization problems is one of the most general approaches how to solve pretty much arbitrary optimization problems. So I could even say that this is a big, powerful hammer for solving optimization problems. Yeah?
Even despite the fact we need to know the gradient of objective function?
Yeah, because if we don't know the gradient, I mean, then we can only use those randomized methods, and they don't even give guarantee of finding the optimum. So most problems that we are usually interested in, they are at least continuously differentiable.
Sorry, as an engineering, we are trying to formulate the problem.
That's also a perfect argument, yes. So there are always different ways how to formulate optimization problems. It is not difficult to formulate a problem which is bad. Okay? It solves the practical situation, but the formulation is just bad. Okay? And there is clever way of formulating optimization problems. So it always takes like a clever approach to the formulation, and there usually you obtain continuously differentiable functions. But yeah, I agree. Not all problems are continuously differentiable, but then we have seen how to use, for instance, the randomized methods, and we will also have a lecture which will show how to solve constrained optimization, basically avoiding the Karush-Kuhn-Tucker conditions, which will allow us to kind of use those randomized methods to also solve constrained optimization problems. So the point that I want to make here is that the Karush-Kuhn-Tucker method is great. It solves pretty much any problem, but there is one big but. Okay? And the but is that it doesn't always work as smoothly as we would expect. And there are two factors which complicate the application of the Karush-Kuhn-Tucker method. The first one has to do something which is called degeneracy. Degeneracy basically, in vague terms, means that we have an overdetermined system. And what I mean by that is that let us consider an optimization problem, and let us introduce some more notation. So let nx denote the number of optimization variables, and I would be the number of inequalities, and we could also have some equalities aggregated in the g function there. And usually, and also in those examples which we have presented in the previous lecture, we always had non-degenerate solutions, which means everything was nicely solvable, and we at no point had an overdetermined system of equations. I mean, if you remember, what we really did was that we investigated all possible combinations of active constraints, and we have done it for the purpose to obtain as many equations as we had unknown variables. Okay? So originally we start just by these two equations. One is the stationarity condition, which says the gradient of the Lagrangian has to be 0. And the second one is the complementary slackness condition, which we know is nonlinear. So remove that one. And we are left just with one single set of equations, but we have more variables. We also need to determine the Lagrange multipliers. So we have more variables than we have equalities. And therefore, we need to add more equations into our system. And those more equations we exactly obtain from those active constraints. So we say, what if we set this constraint to be equal to 0? What we obtain is that suddenly we have new equation from which we can solve for the remainder of the unknown variables. But the problem was the problem is that sometimes we can obtain more equations than we have unknowns. And then we have an overdetermined system and we are in a big trouble. So let me give you a graphical example. Let's suppose that these are the constraints of our optimization problem. And let's suppose that the optimum is here at this vertex. Okay? So essentially what we are saying is that if we now number the constraints like this, what we are saying is that constraints number 4 is active and constraint number 5 is active, which together with the stationarity condition or like this, which together with the stationarity conditions will give us enough equations to determine the optimal solution. Because here we have enough equations to determine x, but we also need 2 equations to determine what are the lambdas, such that we can certify optimality. Okay? So this is the easy case, which we call is the non-degenerate case. Okay? Because we have at most nx constraints which are active at the optimum. So here in this particular case, we are in the 2-dimensional space, so nx is equal to 2. So we have at most 2 constraints which are active. And we know that depending on the shape of the objective function, also this point can be optimal, in which case there is just a single constraint which is active. And we could also have like optimization problem like this, and here at this optimal point, no constraints are active. Okay? So what we can see is that we have at most nx active constraints in this particular case, and this is the easy case. This is easy to solve. Well, taking into account that the constraints are linear, then all equations are linear. If the gradients here are linear as well, what we obtain is just a set of linear equations. So that's easy to solve. The trouble is that, and again it is related to what we have just discussed. What if we formulate the problem in a stupid way? Let's say this is the optimal solution, but I also add a constraint like this. For instance, constraint number 6. This constraint, technically speaking, is redundant. We can remove it completely, and we don't change the position of the optimal solution. Okay, so how do we know the optimum is there? Well, we should also write like what are the level sets of the value function. Okay. So what we can see here is that even if we remove the red constraint, we still obtain the same solution. But let's suppose somebody has also included the red constraints into our problem formulation. Suddenly what we have is that we have 3 constraints which are active at the optimum. And basically, now we have an overdetermined system because we have 3 equations in a 2-dimensional space which should denote the optimal point. Okay? So this case shows a so-called degenerate case where we have more constraints active at the optimum than is the dimension of the optimization space. So the dimension here is 2, but we have 3 constraints which are active at the optimum. And suddenly we have a problem of solving the system of equations because we have 2 unknowns and we have 3 equations.
Because the presumption that at the maximum 2 constraints are active, so we examine 0, 1, or 2 active constraints. I don't see a case when we examine.
Okay. What you can do is let's say we examine those combinations, and what we said is that if we have a convex problem, we have sufficient and necessary conditions. So basically, when we find the first point, we can stop searching for the remainder of the point because we know that they can be at most like the same as the first optimal solution. Okay? So basically, the first scenario would consider independently constraints 4 and 5. The second one would consider constraints 4 and 6, and then we should consider constraints 5 and 6. Okay? In all these cases, we obtain the same solution, correct? But if we need to enumerate all possible combinations of constraints, and if we need to explore them, then the size of the exploration space would be much higher in this case, because we are also exploring kind of redundant vertices. It adds to that, yes, and it basically leads to non-uniqueness of the solution. So, okay, let me be even more technical. We know that if the value function is strictly convex, and the constraints are, for instance, linear, we have just a single optimal solution. Okay? However, here in these cases, we obtain the same solution 3 times. So it basically says, yes, the theory says a strictly convex problem has a single solution. However, this one says that single solution will be found 3 times. So the degeneracy has something to do with non-uniqueness of the solution when exploring different combinations of active constraints. It's still unique.
Value of x and objective function.
Yeah, it is still the same solution. It's just that, the solver probably would need to explore also these. And now imagine that it is not a convex problem, meaning we cannot stop after finding the first solution which satisfies the Karush-Kuhn-Tucker system. Basically, we are just wasting computation by exploring combinations which are just the same. Mm-hmm.
Let's say we also explored only the constraint number 4 active and constraint number 5 active. So we again should find, when we say the constraint number 4 is active, we should find this optimal solution also.
No, because when we are exploring just constraint number, or assuming just constraint number 4 is active, like this, we are also saying that the other ones are not active. So it is not enough to say, let me consider constraint number 4 active. They are strictly non-active, meaning if we would explore this combination, we would for sure not find this point, because here we are assuming the point is not contained in this constraint. It would need to be somewhere else. So just exploring constraint number 4 would not give us the optimal solution. Okay? So usually what we have is that we have these kind of non-degenerate solutions. So there are as many active constraints as there is the dimension of the optimization space. However, in this case here, we have 3 constraints which are active at the optimum, which is more than the number of decision variables which we need to find. Okay, so we have an overdetermined system. And the same situation can also happen in the dual space with the lambdas. Okay, again, we could have more lambdas which are active than that is the dimension of the dual space. So that's a non-degenerate solution. Non-degenerate means nice, easy to solve. However, we could also have degenerate solutions, as we have just discussed, and we actually distinguish 2 situations. We could have the so-called primal degeneracy. Primal means that we have more than nx constraints active in the primal space, in the space of x variables. And we can have dual degeneracy, which means non-uniqueness in the dual space. So basically what you need to remember is, if you attempt to solve a problem using some solver, some software, and the software complains about degeneracy, this is what happened. We had the problem contains constraints which could be removed, and that would suddenly lead to a non-degenerate case. Okay, so essentially, if the solver prints something along these lines, either primal or dual degeneracy, it means there is some non-uniqueness there, and it means some numerical issues, and in critical applications, I would not trust the solution. I would rather look at the problem formulation, try to detect these additional constraints, and I would remove them. Because once the software runs into these problems, nasty things could happen. Okay, you could have some numerical issues. You can have some slight deviations from the optimum. Basically, we always aim for a non-degenerate solution. Okay? So that's the first limitation or the first problem of the Karush-Kuhn-Tucker method. The second problem is that there are many, and saying many is an understatement, many combinations of active constraints that we need to explore if we just apply the Karush-Kuhn-Tucker method. So as we have just illustrated on the whiteboard, again, if we consider NX optimization variables and NI constraints, then we know we can explicitly enumerate what is the number of combinations of active constraints that we need to explore. And in the worst case, again, the software needs to go through all combinations to find the optimal point. If the problem is non-convex, it needs really to go through all possible combinations. If the problem is convex, it starts one combination after the other, stopping once all Karush-Kuhn-Tucker conditions are satisfied. But it can also be the very last combination of active constraints that the software explores, and that one is satisfied. So complexity of the Karush-Kuhn-Tucker method is directly proportional to the number of active constraint combinations that we need to consider. And we know that at the optimum, no constraints could be active. One constraint could be active, two, up to the dimension of the optimization space. Okay? Now, how many are there? Well, let us motivate the result there by a simple example. Let us consider we have 3 constraints and we have 5 inequality constraints. So how many combinations of active constraints do we need to consider or explore in the Karush-Kuhn-Tucker method? Well, no constraint could be active, so like this. One constraint could be active, meaning 1, 2, 3, 4, 5. Each of them is a separate case, okay, so we already have 6 combinations to explore. But 2 combinations can be active, okay, so it could be 1, 2, 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. But we are still not done. I mean, the dimension of the optimization space is 3, so 3 constraints could be active at the optimum. Okay, so 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5, 2, 3, 4, 2, 3, 5, 3, 4, 5. Actually, I'm missing something. 2, 4, 2, 4, 5. 2, 4, 5, and 3, 4, 5. Okay. So basically here we have 1 plus 5 plus 10 plus 10. Okay. So 26. 26 combinations we need to explore. Now what does it mean to explore a combination? Basically to solve a system of equations. If the system of equations is linear, well, that's rather easy. All we need to do is to do essentially matrix inversion, and the matrix inversion is in general operation which is cubic in the dimension of the, well, it's cubic in the optimization variable, so yeah, I mean, we could write something like that. Okay? So that's the number of arithmetic operations we need to perform to obtain a matrix inverse. Okay? But the trouble is that this number here, this 26, that grows very rapidly with the number of constraints and number of optimization variables. And actually, this general formula is just generalization of that particular case. Okay? So we are considering this term here, which says from this many constraints, choose at most this many, so that's the n choose k operation, which is n factorial over k factorial times n minus k factorial. And you can easily verify that if you plug in the numbers from the whiteboard, like 5 for the number of constraints and 3 for the number of states, then 5 over 0, since the index I goes from 0, 5 over 0 is 1. That's when no constraint is active. Then we have 5 over 1, which is 5. Then we have 5 over 2, which is 10. And 5 over 3 is also 10. And then we are summing it up. Okay? So this is the number of active set combinations that we need to explore. And this is actually a huge issue. It is a huge issue because 26 combinations is the case when we have 3 optimization variables and 5 constraints. This is kindergarten problem. This is a toy problem that can be solved by hand. Most practical problems, they involve thousands of optimization variables and tens of thousands of constraints. And now imagine what is 10,000 over 1,000, like n choose k. Just take a factorial of 10,000. I mean, that's a huge number. And even worse, the number of combinations that we need to explore, well, the software needs to explore, grows rapidly. So if we now have 5 optimization variables and 10 constraints, still a tiny case, very easy example, 638 cases. This is still a simple example. 10 optimization variables and 50 constraints, and we have 10 billion combinations that we need to explore. Now, in MATLAB on a notebook, an inverse of a matrix of these dimensions here would take probably 1 microsecond. But then multiply the 1 microsecond by 10 billion, and you are already in this like kind of case of seconds or minutes. This is still a very simple case. This already approaches these dimensions some practically relevant problems. So say 100 optimization variables, 500 constraints. This is 10 to the power of 107. Even the fastest computer on the world would not solve the problem just by enumerating all possible combinations. So what I'm essentially saying is, in the Karush-Kuhn-Tucker method, we need to explore all possible combinations and stopping at the one which satisfy all constraints if the if the problem is convex. If the problem is non-convex, we cannot even stop once we find a candidate. We have to find all candidates. The problem is there are this many possible combinations that the software would need to explore. And just to put this into perspective, the number of atoms in the whole observable universe is estimated to be between 10 to the power of 78 to 10 to the power of 82. In other words, the case, a rather simple case with 100 optimization variables and 500 constraints, has more combinations than there are number of atoms in the whole universe. So even if you would kind of make a computer out of each single atom, it would still take 10 to the power of 20 kind of time units to explore all possible combinations. Okay. So that's the real limitation of the Karush-Kuhn-Tucker method. That it is an extremely nice and general way of solving optimization problems. It is just this little tiny problem that there will be many, many combinations that we would need to explore. Regardless of that fact, there are special cases which use kind of a modification of the Karush-Kuhn-Tucker method to obtain the solution in a more effective manner. And the two typical examples which allow for more simple algorithms are linear programming and quadratic programming. And today we will cover the linear programming, leaving the quadratic programming for the next lecture. Okay? So linear programming is often abbreviated as LP, linear program, or linear programming. And there are different ways how to solve linear programs. And today we will cover the simplex method, which is one of the most popular and most effective ways of solving linear programs. So just to remind you, because I'm sure you know what linear programming is. So in linear programming, what we have is a linear objective function. So C here is just a vector of constants. So this is nothing else than a linear function of the optimization variables. We have linear constraints in the type of equalities here. So here actually in this A and B matrices and vectors, there are actually many constraints which are hidden inside. Okay, so it is not just one constraint, it's actually many constraints. And we have linear inequality constraints. Okay? So the important distinction factor of linear programs from other optimization problems is we have a linear objective function and we have linear constraints. In such a case, we can talk about linear programming, and maybe I would put it now. These algorithms that we will be covering can solve linear programming problems which have 100,000 optimization variables and roughly 1 million constraints. For that formula that I have shown, that would show probably 10 to the power of 10 million, okay, which is unthinkable. Okay. So these kind of linear programs, because we are considering particular case of objective function and constraints, there are algorithms which can solve even large problems of these instances. And linear programming, I would say, is the most used formulation of optimization problems in practice, because there are so effective algorithms to solve these problems. So, of course, you can formulate the problem and you can say, I don't like a linear function. My function is quadratic. Why should I use linear programming? Well, because you can solve even very large problems. There are effective algorithms to do that. And actually, there are many real-world problems which directly can be written as a linear program. And we have seen several of them in the previous lecture. We could have a diet problem. So we need to buy food, or it could be some raw material for the production, such that we minimize the purchase price and we satisfy certain constraints, like the overall mixture has to have certain properties. We are only allowed to buy non-negative amounts of some ingredient and so on. We could have allocation problems that can be directly formulated as linear programming. We could have separation and classification. We will have a lecture on that. We could solve distribution problems directly as linear programs. And basically, there are many, many real-world problems. You will meet them at the exercises. At the exercises, you will solve really large and industrially relevant problems formulated as linear programming. Okay? So linear programming nowadays is more or less a technology. If you come to a manager and you tell him, let's solve this problem as a linear program, he will not discuss it with you too much. He will not be asking questions like, do we have a software for that? Is this really an effective formulation to be solved even for large dimensions? He would probably not ask these questions, because nowadays pretty much everybody meaning an educated person, knows that linear programming can be solved effectively even in very large dimensions. So if we can formulate a problem as a linear program, we can also solve it rather efficiently. So that's the one possible formulation of linear programming. Minimize a linear function subject to linear equality and inequality constraints. Sometimes, however, we don't have equality constraints. We only have inequality constraints. Then we could also formulate linear programming in this form here. We might not need to minimize, but instead we would like to maximize some objective function. So here, minimizing would essentially mean minimize the input energy to our process such that we satisfy certain constraints. Maximizing would mean maximize the profit subject to some other constraints. And we could also maximize linear objective functions subject to also equality constraints. So these are the four most popular formulations of linear programming. Basically, there are different types of software which solves this problem. One of them is, for instance, in Excel. Excel also includes a linear programming solver. Of course, in MATLAB, we have solvers to solve linear programming. The point that I'm making is different softwares, those softwares we will call solver. Solver is a specialized software to solve particular class of optimization problems. Each solver takes a slightly different kind of inputs from the user. Sometimes, so that input, what the solver usually asks you for are, give me C, A, B, and I give you the solution. But you have to be aware whether the solver performs minimization or maximization. You have to be aware whether A and B are for the inequalities or for the equalities. Okay, so for that you need to kind of study the manual of the solver to see what is the input format that you need to provide. So that's point number one. Point number two is how to formulate these problems. How can I take one of these problems and create vector C and matrix A and vector B? So this is what you will be doing at the exercises, because essentially the best way how to learn this is by experience. But let me give you a couple of examples. One of them we have already seen. Previously we have discussed the optimal network flow problem. So at the input node here, we had some incoming source. It could be oil, gas, whatever. The same amount has to be exported at the final node, so there is no accumulation at the intermediate nodes. So that's what these constraints are about. We would like to minimize the price of the delivery through this network. And what comes now is that we can also include inequality constraints. For instance, we can say that each of these transportation channels has some lower and upper bounds on the capacity, such that we cannot under-deliver or over-deliver through that transportation channel. Okay? And these constraints can now be easily aggregated into those A, B, C matrices and fed into the solver, which will then provide the optimal allocation. So that's example number number one. Example number two is, let's consider the following situation. So let us practice the basic task of formulating a linear program. So we are running a company. We are producing two types of products. The first one is a cheap one. We are selling it for €1.5. The second one is more expensive. We are selling it for €6. However, to produce those products, we need to consume some input material, and this is the the weight or volume units of the material that we need to produce corresponding products. And we only have 200 units of the material available. Now, how many pieces or kilograms or whatever of each product should we produce, such that we maximize our profit? That's the objective now. So how do we formulate this problem? So to formulate the problem, we first have to determine the direction of the optimization. Are we going to minimize some quantity or maximize some quantity? So what are we doing here? So we want to maximize. Maximize what?
Profit.
The profit. What is the profit given by? So the profit is the amount of units of P1 multiplied by the price of P1. Okay, so that's 1.5 times. Okay. Even before that, one of the steps that we should take is we should denote our optimization variables. Okay, so I will denote by x1, that will be the amount of product number 2, and x2 would be the amount of product number 2. So 1.5 times x1 plus 6 times x2 is the profit that we achieve if we produce this many kilograms, volumetric units or pieces of product 1, and this is for product 2. But we have constraints. So how the constraints would look like? How many constraints do we have? Do we have 2 constraints? Why 3? I can only see 1 here, though I agree there are in fact 3 constraints. But I agree there are 3 constraints from a practical point of view. Okay? So what is the obvious constraint here? How do we formulate it? So the amount of material must be that we consume must not be larger than 200. Now, how much material do we consume? Well, it's 0.5 times x1 plus 6.5 times x2. 6.5 times x2. Okay. So what are the 2 additional constraints?
We produce non-negative.
Right, so x1 non-negative and x2 non-negative. Now, they are not mentioned here. Actually, they don't even matter in this particular problem at all. Because we are maximizing the profit, and we are essentially gaining profit by only having positive values of x2. Okay? If I would even omit these values, by maximization, I will run into positive values. Not necessarily. Actually, not necessarily. Yeah. We could use, that's option number 1. For instance, let's say that we are actually producing product number 1 at a loss, meaning we are losing money by producing x1, which is like you are obliged by law to produce not only the product that you want to sell, but also a byproduct which is not really effective from the economic point of view, but you are obliged to produce it. Okay?
They said they produce a lot of products as byproducts, and they are selling them underpriced just to get rid of them.
Yeah, that's another possible situation. Okay. So now what would happen is, if we don't include these variables, is that the optimization would in fact set x1 to negative value, right? Because setting x1 to negative value would actually mean that you are kind of out of nowhere creating new material that you are consuming for x2. Okay? So in that case, these constraints would be extremely important. So bottom line is, in most economic problems, we also have these non-negative constraints, even though we don't explicitly mention them here. Okay? So this is phase number 1 when we want to solve these problems. First, we need to formulate them. Once we formulate them, we convert them to some standard form, and we call a solver which will just return the optimal solution. Yeah, sure.
Those formulations, first and last, where is non-negativity condition. Do we need to add them to the solver which is designed?
Yeah, because usually well, again, it depends what kind of solver, what kind of input format it takes. If it takes the input format, and let me go here, if it takes this format here, where it explicitly says, I will assume that each decision variable is non-negative, then essentially what you provide to the solver is just C, A, and B, and it will implicitly assume non-negativity of the variables. But if you have such a solver, and you want to solve a problem which has non-negative variables, which you know are non-negative, then you must do additional transformations to actually be able to use this solver. And we will come back to those reformulations in a second. Okay? So we have to know which of these 4 input formulations our solver expects, because then so if the solver only expects this formulation, we need to include those negativity conditions into the A and B parts. Okay. So that's example number 2. Now let us consider example number 3. So actually, sorry, now pretend that you have not seen anything. Okay. So we are running a pub. and we need to buy, or we want to buy, a light beer and a dark beer. We know that the light beer we are buying at €1 per liter, selling it for €2 per liter. The dark beer, it's more expensive to purchase, but it's also, we are gaining more profit on that. However, we have these two conditions. So obviously, we would only like to buy dark beer, provided that we have guarantee that we will sell as much beer as possible. Actually, this is an example from the Simpsons series. Okay, so there is Homer. Homer drinks an arbitrary amount of beer. Okay, so Joe, what he wants to do is to essentially come up with an optimal composition of the beer, such that he maximizes his profit. However, the Duff Company does not allow him to buy only dark beer. What the Duff Company said is, if you want to buy 1 liter of dark beer, you have to also buy at least 2 liters of light beer. Meaning, if Joe buys 2 liters of dark beer, he needs to buy at least 4 liters of light. He can also buy more. He can buy 5, 6, 7, 8. Okay? But at least 2 liters of light per 1 liter of dark. And the Duff Company will not sell him more than 3,000 liters in total. And now we have to come up with the optimal composition of light and dark beer, such that we maximize our profit. Okay? So let us formulate the problem. Again, step number 1, determine what the optimization variables are. Okay? So obviously, so what are we going to do is we will have x1, or rather XL, that would be for the light beer, and XD would be for the dark beer. Okay? Now, direction of the optimization. Are we going to minimize or maximize? Maximize. Maximize what? The profit. What is the profit given by? 1XL. I'm just writing what you are saying. Plus
1.5 XD is the profit.
Okay, so we are making the difference of those two numbers and the difference of those two. Okay, so that's the profit for 1 liter of each beer. I would maybe even write it in a kind of more illustrative way like this. It doesn't. Yeah, I mean it's the same numbers. Okay. Now comes the funny part. Sorry.
Even if you maximize 2 and 3, you should get same axis. Okay, different value of cost.
Maybe. Maybe also a different optimal solution. But you see, in a linear function, I mean, you can essentially, if you would change these coefficients, you start changing the tangent. Then it's the same thing. Yeah. Okay, so let us now write this constraint. This is the tricky part. How would you write it? Tell me.
XD equals 2XL.
Okay, so that would mean if I buy exactly 1 liter of dark beer, I buy exactly 2 liters of white. But I don't need to buy exactly that amount, but at least 2 liters of light beer per 1 liter of dark beer. So the devil is in the details. So in other words, this constraint would not be an equality constraint, it would be an inequality. In which direction? Would this be greater or smaller sign?
Smaller.
Like this? So does it hold? So if I buy 2 liters here, I buy 4, but I can also buy 5, and the relation holds. Okay? So that's okay. How do we write the final constraint?
XL plus XD.
Plus XD